have an in-present presentation, and the paper is Hierarchical Latent Relation Modeling for Collaborative Metric Learning, and the presenter is Viet-Anh Tran. So the stage is yours.
Thank you very much. So, hi everybody, my name is Viet-Anh Tran from Deezer. I'm really glad today to introduce our work on latent relation modeling from implicit data. Here is the outline of my presentation. And in this work, we concentrate on the top K recommendation, where we observe a set of positive implicit feedback, such as click or stream. And our goal is to recommend K most relevant items for each user. For example, you can see here the top 5 playlists, recommended playlists in the user's homepage at Deezer. In this setting, recently, metric learning-based methods such as CML show competitive results compared to the classic metric factorizations. In CML, CML embedded users and items in the same metric space, where distance between users and items are used to measure the similarity between entities. And it adopts the triplet loss to learn the vector representation, ensuring that the distance between users and the items they do not interact with is larger than the distance between users and the favorite items by a positive margin M. However, CMN has a main limitation that each user is represented by a single vector in the vector space that fail to capture the heterogeneity in user-item relations. That means a user cannot be simultaneously close to 2 distinct items in the vector space. That's undesirable because same user could listen to the music from the very different genre, such as rock or classic music, depending on the context of working or sleeping. CMN does not take into account the relation between items also. However, in the user preference on the item could depend on the items they already interacted in the past. For example, user could listen to the new songs coming from the artists they already like in the past. So to overcome this limitation, the current recent research try to learn an additive relation vector RUV by using the translation methods in the knowledge graph domain. For each user item pair U and V, it permits to translate the vector user PU to another vector PU plus RUV so that to capture the heterogeneity in user item relations. Notably, Tay and An propose an RMRAN implicitly learned this vector by means of memory network, while another work, Park and An propose TransCF to explicitly learn this vector through the information from the neighborhoods in the bipartite interaction graph. However, these methods just concentrate on the user-item relations, but it ignores the relation between items. And on the other hand, Zhang later proposed other CMN, which learned this vector from the relation between the candidate items and the items the user already interacted previously. However, this work just in contrast, just concentrate on the relation between items and ignore the heterogeneity exists in user item relations. So from that observations, we argue that both user item relations and item relations complement and influence each other, and jointly consider both user and item, both type of relation could bring the fine-grained user preference. And there exists also a hierarchical structure between these relation types. So in the next section, I will present our proposition to incorporate these observations. So the first component of our model is the relation modeling based on the memory network as proposed in LIML. The memory network composed of two components. The memory key should represent the relation types, while the memory slot M should represent the vector value corresponding with the relation types. And the relation modeling contains three layers. The first layer is rank embedding, combine the two input entities. And then the attention layer will calculate the attention weights for each memory slot from the rank embedding and the corresponding memory key Ki. And the final layer will extract the relations by weighted sum of all memory slots. And here is the first, the architecture of the first models that we propose from the observation that users might predominantly forge their opinion about an item from the relation between this item with the items that the user previously interacted with. So from that, we built the relation between user and items on top of relation between items through the module of user attention. Specifically, the relation between items are modeled by memory network M, and then the relation between user and items is the weighted sum of the relation between the candidate item V and all the items that the user U already interacted with. And the weights are extracted from the attention mechanism. Then the similarity between user and items are just the Euclidean distance between the item V and the translation of vector, user vector PU plus RUV. And we use triplet loss as in other CMN extension. We also consider another extension of our proposed model in this model called HNR++. And in this model, we add another item attention module, asymmetric to the user attention module in the previous model. This model is for building the item-item relations on top of the user-item relations from the observation that sometimes items might be related together, not only because of their characteristic, but also because some users consider them together in the specific context. It is very frequent seen in the music domain where some users might listen to the specific list of songs while running, while working, for example. And the final representation of relation U and V is just only the sum of the output of these two attention modules. To validate our proposition, we consider 4 data sets that I list here after 10 core preprocessing process, and we ordered by density, the decrease of density of the user item interaction data. For each data set, we use random splitting, and 80% of the user interaction are used for training, 10% for validation, and the last 10% for the test. And we report here 5 metrics, accuracy metric, 5 accuracy metric, and we use median popularity of recommended item for the popularity bias. And we compare our proposed model with 3 groups of baseline, the models with our relation modeling, the model using just only user item relations, and the models that use only item-item relation. So the first, on the relevance of the relation modeling, we can see that all the models that incorporate relation modeling in red, modeling in red significantly outperform all the models which do not use it in Movie Lens, Econess, and Yep. However, we can see that the benefit of this relation modeling tends to decrease on the sparse data set. For example, it's narrow in the Yep data set, and on Amazon, we don't see any benefits. We postulate that it's possible that in the case of very sparse data set where we have only few interaction, the relation modeling by latent memories could bring noise and more prone to overfitting. And on comparison between 2 types of relations, we see that the model which use relation between items outperform the models use user item relation. This result shows that user preference for an items could strongly depends on the items that the user already interacted in the past. And on comparison between our proposition with other extensions of the CMN, we can see that our model outperform all others attention of CNN on movie lens, EchoNet, and YEP. However, we don't see it in the Amazon. Our models are outperformed by other CMN. It's possible that in this case, because of the other CMN use relatively simply strategy for relation modeling comparing ours. And despite that, our models outperform other CMN in the 3 other dataset. It's be outperformed by other CMN in the last case. And comparing between 2 models, we can see that the HNR++, which use an additional item-item relations, outperform the HNR, especially in the case of movie-lens and EchoNet, which show that the item-item relation could be built on top of user item relations, especially for the data set where the contextual information is really important, for example, in movies or in music. However, we do not see that in the YEP and Amazon. It's possible that the 2 kinds of business product and book, they are more prone to contextual information. And finally, for the bias, popularity bias, our model proposed less popularity bias comparing with other attention of CMN and baseline. On the movie lens and EchoNet is a desirable property of recommendation, but in the YEP and Amazon, we are a little bit more popular than the other extension of CNN, but far better than RLS compared to RLS, popular metric vectorization. So to conclude, in this work, we show that the complex user interest could be captured by jointly modeling latent user item and item-item relations just from the implicit data. However, relation modeling does not always improve the standard CML, especially on the sparse dataset with very few interaction data. This also opened the door for the future work with challenging sparse dataset, and we also consider to extend our work for the sequential recommendation. For example, you can see here for the flow product in Deezer. So thank you very much for your attention, and I'm ready for the question.
So thank you, Viet-Anh, for your presentation. I have really a lot of questions I would like to ask you, but I will give the precedence to the audience. Okay. So there is a question from the online participants about asking if you did compare your approach with graph-based neural networks and in terms of architecture and structure.
Yeah, that is a good question. At the moment, we just compare with other extension of the CMN because our works, we consider that is another extension of this model. So at the moment, we just consider the baseline from the CMN. But that is really good so that in the future, we will compare our model with other graph-based recommendations.
Okay, thank you. Are there questions from, well, I take the opportunity to ask some of my questions. Okay. The first one is, I'm curious to know if this idea of this hierarchical latent relation, if it applies, if it can be used also for similarities which are not based on metric. I'm thinking about cosine similarity. So I'm just curious to know if there is it is possible to apply this approach also to non-matrix similarities.
I think that the idea of the hierarchical it's possible that it independence with the similarity that so we can use that for the metric-based methods, but we can use also for the dot products-based methods. Some others that it's possible that there are some kind of methods based on another kind of space. For example, hyperbolic space is already incorporated some kind of notion of hierarchy in the space already. So I think that for the dot product, yeah, we can use that.
Okay, thank you. Are there questions from the audience? It seems not. So thanks again for your presentation, and I will later look for you to ask more questions offline.
Okay, thank you very much.